Elements in the periodic table, introduction to atoms. We're going to specifically go through how did the atomic theory develop. We'll talk about Dalton's atomic theory, Thomson's model, Rutherford's model, the cloud model, and then specifically we'll look at the modern model of the atom, and in that area we'll talk about particle changes, comparing particle masses, atomic number, and isotopes. So how did the atomic theory develop? So for centuries we were really curious about what makes up matter. Until recently we have only been able to speculate toward what matter was made of. Previously we actually thought that the materials that made up all things on the planet, they came from four major elements. Those four major elements were earth, fire, wind, and water. Obviously that is not correct. We have revised that over quite a few millennia. After discovering that atoms are the basic building block of all matter, scientists tried to build models of the atom. Some of the models are shown right here in this picture. We worked from the least complex on the left all the way to the right, which are the most complex and the more modern models of the atom. And everything in between is kind of what we progressively worked from and then to. The models have changed many times over the last 100 years. I put this picture inside of your notes to show what specifically occurred with the models and the changes that occurred in those models from the early 1800s until around the 1920s when we really reached the modern model of the atom. Around 430 BC, the Greek philosopher Democritus, he proposed that matter was formed of small pieces that could not be cut into smaller parts. So he thought that all pieces of matter you could take, you could cut them up into itty bitty teeny tiny pieces, and you could continue to cut them until they were smaller and smaller and smaller. But eventually you would get to a point where you couldn't cut those pieces of matter any smaller. They were the smallest unit. And he used the word atomos, which meant uncuttable. So he used that word to represent the smallest possible pieces of matter that existed. And we have adapted that term to modern English, and we've used the term atom to describe the smallest piece of matter that is uncuttable. So in modern terms, an atom is the smallest particle that still can be considered an element. We do have materials that make up atoms. We call those subatomic particles. The idea of atoms began to develop again in the 1600s as people did experiments. And as you are going to notice when we start talking about science, a lot of times we're going to talk about how knowledge is built upon prior knowledge. So the atomic theory grew as a series of models that developed from experimental evidence. We took some experiments and we built models. And then we performed new experiments and adapted those models. So as more evidence was collected, the theory and models were revised, and they became updated, and they became more correct based on the evidence that was presented in new experiments. Dalton's atomic theory. John Dalton was an English chemist that used evidence from a variety of experiments to infer that atoms had a number of different characteristics. He thought that atoms were like smooth, hard balls that could not be broken down into smaller pieces. So he thought of them kind of like marbles.
She likes the word balls.
The main ideas to his theory. He thought that all elements consist of atoms that cannot be divided. So that was similar to some of the previous ideas. He thought that all atoms of the same element are exactly alike, and they have the same mass. Atoms of different elements are different and have different masses. So all of the hydrogen atoms would have the same mass. They would be the same size. All the carbon atoms would be the same size. A carbon atom would have a different mass from a hydrogen atom or an oxygen atom or a nitrogen atom. He thought that an atom of one element cannot be changed into an atom of a different element by chemical means or by a chemical reaction. A carbon atom would always be a carbon atom. A nitrogen atom would always be a nitrogen atom. And you cannot change those based on any type of chemical reaction. He thought that compounds were formed when atoms of more than one element combine in a specific ratio. So for example, water. Water is a compound. Water is made up of one oxygen atom and two hydrogen atoms. The ratio is 1 to 2. One oxygen atom to two hydrogen atoms. So it would be a compound. Compounds can be broken down. We can remove atoms from a compound. When we remove atoms from a compound, it is no longer the same compound. Thomson's model. In 1897, J.J. Thomson discovered that atoms contain negatively charged particles called electrons. So he made that discovery. There's some negative charges that are floating around inside of an atom, and he called those negatively charged particles electrons. Here's a picture of Thomson. Scientists knew that atoms themselves had no electrical charge. So based on these two facts, based on the fact that Thomson discovered that there are some negative charges floating around inside of an atom, and based on the fact that scientists knew that atoms themselves had no electrical charge, what can we conclude? We can come up with a conclusion based on these two pieces of information. What can we conclude based on those two pieces of information? Thomson reasoned that atoms must also contain some sort of positive charge. The positive charge must balance the negative charge of the electrons. The atom itself does not have a positive or a negative charge. It is neutral. Knowing that an atom does not have a positive or negative charge, and knowing that pieces of the atom are negatively charged, there has to be a positive charge that is counteracting the negative charge. Thomson proposed a model that had electrons scattered throughout a ball of positive charge. And he thought of it as being much like the seeds in a watermelon. So here's a picture of his model that he designed. So we've got a ball that is mostly positive charged with a whole bunch of small negative charged particles floating around in it. The element in nature that he thought that most likely represented would be a watermelon. The seeds would represent the negatively charged electrons, and the fruit itself represented the large amount of positive charge, the ball of positive charge that was found inside the atom itself. In 1911, one of Thomson's former students, Ernest Rutherford, found evidence that challenged Thomson's model. There's a picture of Ernest Rutherford as a student. Rutherford's research team aimed a beam of positively charged particles at a sheet of gold foil. So they took a particle emitter, they shot some positively charged particles at the sheet of gold. He and his team predicted that if Thomson's model were correct, the charged particles would pass straight through the foil. He thought it would just shoot right straight through. They also predicted that the paths of some particles would bend or deflect slightly. The particles would only slightly deflect because the positive charge was thought to be spread out in the gold atoms. So they thought most of the particles that would get shot at the gold foil would pass through. Some of them would be slightly deflected. Rutherford observed that most of the particles passed straight through the foil with little or no deflection, much like they hypothesized. To everyone's surprise that was performing this experiment, a few particles were deflected by the gold foil at very large angles. So many of them actually came right straight back the direction they came from. So they deflected at really weird angles, and that was not expected. Based on the results of his experiment, Rutherford suggested that the atom is mostly empty space, but it has a positive charge at its center. This is a picture of what Rutherford thought the atom looked like. He thought it had a positive charged center, and around that positive center were these negative charged electrons, and a lot of the space in between the positive center and the electrons was just empty space. So we know that like charges repel each other. When you take a magnet and you put a positive end of a magnet to a positive end of a magnet, they push one another away. You put the negative side to a negative side, they push each other away. So like charges repel each other. So Rutherford inferred that an atom's positive charge must be packed with a small region in its center called the nucleus. So inside the nucleus, there's some positive charges. Any particle that was deflected strongly had been repelled by an atom's nucleus. So he thought that central area where there was a positive charge, when a positive charged particle was shot towards the atom, it would come close to that positive charged nucleus, and it would get deflected back pretty much the direction that it came at very large angles. So Rutherford developed a new model of the atom, and his new model looked a lot like a cherry with a pit in the middle of it. And so he thought that the area where the pit was at would be like the nucleus, where there was a whole bunch of positive charge, and then the rest of the fruit was the space that was taken up by the electrons. So that outer fruit area, the electrons would kind of flow around in that area. Later research suggests that the nucleus was made up of one or more positively charged particles. Rutherford called the positively charged particles in an atom's nucleus protons. Those positively charged particles were termed protons. Bohrs Model. One of Rutherford's students was Niels Bohr. He was a Danish scientist. In 1913, he revised the atomic model again. He suggested that electrons are found only in specific orbits around the nucleus. The orbits in Bohr's model, they looked like planets orbiting the sun or the rings of a tree. Each possible electron orbit in Bohr's model has a fixed energy. The next model is the cloud model. In the 1920s, the atomic model changed again. Scientists determined that electrons do not orbit the nucleus like planets, as Bohr had suggested. Instead, electrons move rapidly within a cloud-like region around the nucleus. An electron's movement is related to its energy level, or the specific amount of energy that it has. Electrons at different energy levels are likely to be found in different places. So what is the modern model of the atom? In 1932, English scientist James Chadwick showed that another particle existed inside of the nucleus of an atom. This particle was called the neutron. It was hard to find because it had no electric charge. It was neither positive nor negative. It was neutral. Additional experiments have led scientists to believe that at the center of the atom there is a tiny, dense nucleus containing protons and neutrons. Around the nucleus is a cloud-like region of moving electrons. Most of the atom's volume is the space in which the electrons move. This space is huge compared to the space taken up by the nucleus. So if the nucleus of an atom were the center of a football stadium, it would be the size of a pencil eraser. The electrons would extend all the way out to the top row of seats. Now, research supports the modern model of the atom. However, scientists still do not know the details of the smallest scales of matter. Particle charges. In an atom, each proton has a positive charge and is written as a plus sign. Electrons are shown by the symbol E negative. According to the scale used for measuring charge in atoms, protons have a charge of +1. Electrons have the exact opposite charge, so electrons have a charge of -1. In most atoms, the number of protons equals the number of electrons. As a result, the positive charge from the protons equals the negative charge from the electrons. So the charges balance, making an overall neutral atom. Neutrons don't affect the charge of an atom because they have a charge of 0. They do, however, affect the overall mass of an atom. Comparing particle masses. Although electrons may balance protons charge for charge, they can't compare when it comes to mass. It takes almost 1,840 electrons to equal the mass of one proton. That is equivalent to the difference between the size of a penny and the size of a bowling ball. A proton and neutron are about equal in mass. Together, the protons and neutrons make up almost all the mass of an atom. Atoms are so small that we cannot use the standard metric system to measure their mass. Instead, we use atomic mass units, or AMUs. A proton or a neutron has a mass equal to about 1 AMU. Particles in an atom. An atom is made up of protons, neutrons, and electrons. So using this chart, what is the correct charge for each atomic particle? So a proton, its symbol is P+. It has a mass of 1 AMU.
its overall charge is +1. A neutron, its symbol is N. Its mass is 1 AMU. And its charge is 0. It does not have a charge. An electron, its symbol is E negative. Its mass is 1/1840th. And its charge is -1. The atomic number. Every atom of an element has the same number of protons. For example, every carbon atom has 6 protons and every iron atom has 26 protons. The number of protons in the nucleus of an atom is the atomic number of that element. So for example, carbon, its atomic number is 6, therefore it has 6 protons inside the nucleus. The mass number of 12 tells us the number of protons plus the number of neutrons. Another representation here, the atomic number here of 28. It is the number of electrons and the number of protons. The symbol name, the atomic mass, and it is written in AMUs or atomic mass units. The definition of an element is based on its atomic number. Carbon's atomic number is 6 and iron's is 26, as previously mentioned. Isotopes. All atoms of an element have the same number of protons. The number of neutrons can vary. Atoms with the same number of protons and different numbers of neutrons are called isotopes. An isotope is identified by its mass number, which is the sum of the protons and neutrons in the atom. The most common isotope of carbon has a mass number of 12, so 6 protons plus 6 neutrons, and is written as carbon-12. This picture shows a number of the different elements or the different isotopes of carbon. Carbon-12, carbon-13, carbon-14. About 99% of the naturally occurring carbon is carbon-12. 99%, 6 protons, 6 neutrons. We do have situations where carbon-13 is found. It is 6 protons, 7 neutrons, and it occurs in about 1.1% of the time. And finally, a very small portion is carbon-14, which is 6 protons and 8 neutrons. 2 other isotopes of carbon-13 and carbon-14 occur, as we just saw. Despite their different mass numbers, all 3 carbon isotopes react the same way chemically. So, isotopes of carbon. All isotopes of carbon contain 6 protons. If they contained a different number of protons, then it would be a different element. So they all contain 6 protons. They differ in the number of neutrons. Fill in the missing information for each isotope. So obviously carbon-12 has 6 protons and 6 neutrons. Carbon-13, because it has a total mass of 13, it must have 7 neutrons. 6 plus 7 equals 13. Finally, the last form of carbon, we have 6 protons and 8 neutrons. 6 plus 8 gives us a total of 14 for the mass. So in this case, carbon 14 is when there are 6 protons and 8 neutrons.